From smartphones to laptops, from power tools to electric cars, batteries are currently shaping the backbone of our modern society. However, batteries are currently at the center of a growing environmental dilemma. They are critical to the global shift away from legacy fossil fuels, but the systems that produce and dispose of them are deeply flawed. As we currently see it, mining for battery materials is destructive, manufacturing is energy intensive, and disposal is poorly regulated. As battery use continues to expand into nearly every part of our life, from smartphones to electric vehicles, the ecological costs grow with it. To discuss this topic, I spoke with friend and undergraduate researcher at Tennessee Tech, Isaac Legault, who has worked on developing new solid-state battery technologies in conjunction with Oak Ridge National Laboratories and the University of Tennessee.
I went to college. I'm still going to college at Tennessee Tech. I'm pursuing my mechanical engineering degree currently. I plan on doing a material science PhD in the fall of 26. I worked in material science at University of Tennessee and Oak Ridge, and I was working specifically with solid-state batteries, and I was analyzing solid-state batteries with spectroscopy.
Before we continue any further, it is important to distinguish between the three main types of rechargeable batteries that we commonly see in consumer electronics. Lead-acid batteries are the oldest type still widely used today, primarily in traditional car batteries. They are bulky, but highly recyclable and supported by well-established collection infrastructure. Lithium-ion batteries are standard in everything from smartphones to electric cars, dominating current commercial markets. They offer high energy density, but come with serious environmental and ethical concerns tied to their production and disposal.
Lithium is quite good at processing and performance. However, safety is obviously concerned with blowing up.
Lastly, sodium-ion and solid-state batteries are newer technologies designed to reduce reliance on rare materials and improve safety. While they are not widely available yet, they represent a potential future standard for energy storage.
Sodium is the top contender in research right now, mainly because it has really good safety and its processing is easier. However, sodium's main problem is performance, as it has really weak output.
Extracting the raw materials needed to manufacture these batteries, particularly metals like lithium, cobalt, and nickel, carry significant ecological costs. These metals are typically sourced through large-scale mining operations, oftentimes in countries with minimal environmental oversight. Whether it's lithium brine fields in arid South American salt flats, cobalt strip mines in tropical Congolese forests, or nickel pits near essential waterways, the end result is the same: massive land disruption, high water use, and heavy carbon output. Beyond carbon emissions, the ecological fallout from these mining operations includes contaminated soil, disrupted water cycles, and the bioaccumulation of toxic metals in food webs. Once introduced into the environment, metals like cobalt, nickel, and lithium do not remain isolated. They move through soil, seep into groundwater, and accumulate in plants and aquatic organisms. These effects undermine the health of entire ecosystems, impairing reproduction in fish, altering the stability of microbial communities, and contaminating the very systems locals rely on for clean water and food production. The damage is not confined to mining sites, however. It radiates outward through biological systems and across political borders. But there is some good news. Currently, lead-acid car battery recycling programs demonstrate one of the highest rates of reusable and renewable material practices in a commercial market, with car battery recycling rates soaring above 99% in the United States, an outlier amongst battery types. And this is not an accident. It's the result of decades of targeted policy and infrastructure. Consumers are often required to return their old batteries when buying a new unit, with private retailers and mechanics being offered financial incentives for their recycling habits. However, if we compare this to the recycling rates seen for lithium-ion batteries, the current leader in market space, we see a completely different story. Currently, only about 5% of lithium-ion batteries are recycled globally. Why is this? Well, the answer is multifactorial. However, it largely relates to the nature of their construction. They are glued together, wrapped in fireproof barriers, and highly flammable. Recycling these batteries safely is hard and expensive. As recycling rates remain low, lithium-ion batteries pile up in landfills, leaking toxic metals that drastically alter soil chemistry. Fungal networks, plant communities, and insect populations, all critical for forest health, suffer, with nearby water bodies seeing pH changes and toxic metal buildup. The impact cascades through food webs. But we are not stuck. Sodium-ion and solid-state battery technologies both represent the next step in potential future energy storage. These batteries are built around safer materials, non-flammable electrolytes, and the goal of decoupling energy storage from high-risk, high-pollutant supply chains. They reduce dependence on critical minerals like cobalt and lithium, making them less vulnerable to global shortages and geopolitical bottlenecks. In theory, they are also easier to recycle and safer to operate, less prone to thermal runaway and degradation. What they lack for now is scale. These technologies remain relegated to laboratory development or early-stage manufacturing, with current production being far too costly to meet consumer needs.
There's issues with how to match the actual energy density and actual proper flow of ions in a solid-state battery.
Until infrastructure catches up, they remain a promising yet incomplete solution, addressing the issues of supply chain instability, fire risk, and end-of-life disposal. These next-generation solid-state batteries aim to replace rare or hazardous materials with safer and more abundant ones. The promise lies in simplifying manufacturing and recycling without sacrificing safety or lifespan. Even if these future technologies catch up to consumer demand, batteries alone will not solve the problem. Electric vehicles in particular illustrate the broader challenge. While EVs entirely eliminate direct tailpipe emissions, their batteries still require these same resource-intensive manufacturing processes and rely on local electrical grids for power, regardless of their ultimate energy source. That said, they remain essential for transitioning to a fully renewable, green energy infrastructure. Electric vehicles come with some hefty upfront costs, both financially and environmentally. The manufacturing of electric vehicles releases far more carbon dioxide than the comparable production of an internal combustion engine automotive, with some EVs producing double the CO2 of their gas-powered counterparts by the time they roll off the assembly line. This comparison begins to break down, however, when vehicle lifetime emissions are considered. In the United States, the average EV breaks even in emissions after only about 15,000 miles. After that, every mile is cleaner than a gas car. This statistic is heavily dependent on the composition of the local power grid, however, as in places such as China, with a larger EV market, yet still largely coal-based power grid, it can take up to 73,000 miles to break even on emissions. The cleaner the grid, the better the payoff. This, however, still far outperforms any current commercial combustion engine vehicle, with modern EVs boasting an energy efficiency that would be equivalent to a 93 mile per gallon gasoline car. Overall, batteries are central to the clean energy future, but the way we mine, use, and dispose of them will shape their impact. A truly sustainable battery revolution means designing smarter energy storage methods, building safer infrastructure, and protecting ecosystems along the way.